All right. I guess welcome to our first makeup class. With the so many holidays we got this semester. Uh, Today we'll basically wrap up the functional programming part of the course and talk about the last topic that actually there's one more topic that are related to Scala, but I want to keep it for the parallel programming part. But right now, let's wrap up the topics we are going to need for the midterm. And the topic is called Future and Promises. And I will promise you, actually, pun intended, that this is something that would work in a similar fashion as the human definition of future and promises. All right. So if you have that in mind, I think it would make it a lot easier to understand the concepts today. And these are one of the good concepts to learn before we transition into parallel programming because this allows many things to be done in parallel. So before we begin talking about the future and promises, let's actually do some quick recap, right? So we talked about the type system on last Tuesday, and we kind of like talk about basically the type system is a prediction, right? It's a prediction that the outcome of an expression and the property is gonna be leading into this type. Integer, for example, we have a constraint that has to be a whole number. A string has constraints that it's just basically a series of character, right? So this is known during compile time, unless something crazy happened to the computer system, like say you have a bit flip and your computer run into a blue screen. Crash, reboot, right? You are you are going to be able to predict that your function call is gonna lead to that type. If the expression is a string type, for example, it will eventually evaluate to a string. This is also partially why when you have exception handling, the type of the exception will be the type that still match here because functional programming is a strongly typed languages. So at the end of the day, if you have to raise exception, you will want to make sure, you as in like the scalar language will want to make sure that type hold, right? This allows the compiler to make a lot more assumptions. This allows you as a programmer to make a lot more assumptions. This also allows the system as well as the architecture, like the hardware itself, to make assumptions. Fun fact: I was reading like a paper with my graduate students and a few more researchers, including a John on actually like how can we use concept, for example, future, right, to actually aid in packet processing, for example, right? These allow basically you to make a lot more assumptions about what is going to happen to this expression. And to define a new type in Scala, because we don't want to be limited to just integer, string, boolean, pair, list, set, right? You can define a class, new trait, new objects by this particular syntax. You can also do type and your own type, right? And each type comes with a rule, right? The rule can be a whole number, that's be an integer, right? It can be a rational number, right? So these are basically the generally two kinds of like also the constraints about the type. Like we kind of cover this concept called upper bound as well as the lower bound. These dictates the hierarchy of types. For example, the traversable type, basically you can go through something, a collection, right? You can go through a collection. So a collection that's traversable, it means that you can iterate through them. Will be something that a list can extend from. A list will be also traversable, but it also has a specific meaning. What does it mean to be a list? Right? A list and a set, whether both of them are traversable, but they are not the same. A list can have duplicate items, a set will not, right? You also talk about variance, where if you want to parameterize the type then a variance has basically dictated the fact that if you can call a function on the type A, a higher kind type CA is said to conform to CB if you can assign CB to CA with no error. The key here is there's no error, right? Sorry. And there are three types of variance. The most obvious one is invariance. Basically, well, if A is equals B, the two types equal. So C of A will conform to C of B for sure, right? Covariance is if A extends B, then C of A will be conforming to C of B. Contravariance is the inverse of this. That's why covariance we use the plus sign and contravariance is the negative sign. So there's an example. A list of cats is a subtype of a list animal. So a function that return a list of cats type parameter is a covariance is a function that returns a list of animal. Contravariance is, let's say you have a string given that return a string given a cat, right? Then it's called contravariance with the parameter for a function that returns a string given an animal. Basically, it is a reversal of covariance. We talked about before we end on Tuesday, we talked about dependency injection, where you might have heard this from software engineering. Basically, this allows you to define A has to finish before B. You inject that dependency. We can decouple the actual implementation. I just going to tell this process A has to finish before process B, but I'm not going to implement it yet. There's some dependency happening, right? This is basically in software engineering. In functional programming, we can use dependency injection to basically tell the program semantics to actually say, hey, I have this function call. I'm not going to implement the detail yet, but it's going to depend on this specific method and I can use it. I just declare that I can use it. I can use it, but right now I'm not implementing it yet. I can implement it later in the next like 10 lines. That's fine, right? We go through an example here in the use case. Let's just say X is a class X needs some database connection, but I'm not implementing it yet because I'm still waiting for my client to figure out what type of database it is, what's the host name and things like that. So I don't really know. Right? But I can still implement the function call that based on this database connection. It creates a dependency, but the dependency is coupled to it's actually now not coupled to that particular database, right? Dependency injection aim to separate out these two processes. You just define, hey, it's going to depend on this connection. Once the connection is established, I will run this. Right? So that's the concept behind. All right, so that's for the recap of what we covered on Tuesday. For more detail, feel free to check out the previous video. Today, we will talk about future and what does the concept of future enable us to be able to do things that are in the parallel programming world. Before we understand that, let's actually talk about the potential benefit, right? Potential benefit. Anyone here heard of the word blocking calls or just blocking in general in computer science? Anyone here heard about that before? So quick question. We all used Fibonacci before, right? F of n equal f of n minus 1 plus f of n minus 2. So if I want to compute f of n, which function do I have to finish before I can finish f of n? So if I want to do f of n for Fibonacci, fifth of n, the Fibonacci of n, yes, basically you need to kind of finish f of n minus 1 and f of n minus 2, right? So the concept of blocking call is basically it's a part of the program that has to finish before the next part begin. Why is it again? Sometimes it's because of dependency. You need to get the data before you can run the next part, right? So why is this bad for performance for parallel program? Anyone want to take a wild guess why this can be bad for performance? Yeah, basically these kind of by default, right? You enforce the sequential order of things. When you talk about parallel performance or parallel program, you want to be able to do many things together, right? But let's say you have 4 tasks, 1, 2, 3, and 4, and you have 4 processors, right? Your ideal goal is I'm gonna map task 1 to processor 1, task 2 to processor 2, task 3 to processor 3, and task 4 to processor 4, right? But what if I tell you task 3 cannot begin until I finish task 2? If you buy a 4-core CPU, can you utilize all the 4 core at once in this case? The answer is no, right? Because you need to finish 2 before you can start 3. So this is basically what one of the things. I'm not gonna say everything that is going to be limiting your parallel program's performance, but this is a key factor. This is a big factor, right? Let's go through some example, right? So let's actually go through uh a more like real life example. I want to make coffee. Let's say I want to make coffee. What's the first thing I have to do? And let's assume, right? I can pour the water into my coffee machine. I can go grind the coffee into the coffee ground, right? Then I basically need to put that grounded up coffee and make an espresso, right? So what can I do in parallel? And what has to be done before the other process begins? Yes, I can boil the water while I'm grinding coffee, right? Both of them, I have both of the machinery to do, so I can just hit the button and then I just wait for both of them. So I can do 2 of them in parallel. Yay, right? So I cut the time by half, depending which one finished first and which one finished last. That'll be the time it takes to grind coffee and boil water, right? And then I will have to wait until both of them finish before I can make my coffee, right? So that means I can essentially do grind coffee. For some reason, I cannot write on the slide. Grind coffee and get water. And this can be done, this is time, right? This can be done in parallel. And then once I finish, and then I can make coffee, right? It means that grinding the coffee and getting water block my process of making coffee, right? And this is a really common thing in computer science and more parallel program. So let's actually go through more example that now involve an actual program. I'm going to show you the code. You can download the code on Canvas as well. You do go to Canvas file, and there's like I think lecture 11 example and lecture 11 example better. Right now we're going to talk about lecture 11 example.scala. The thing here is I'm going to show you the code on the screen in a bit, but let me kind of finish the slide to explain what the code entails. Basically, the code, what it does is it look at the list of URL, basically a little web page URL, right? And then the code will look at that and count the number of occurrence of certain words. So if I give you 5 web pages, and I want you to count the number of times I see the word cat, can I do can I go through 5 pages in parallel in theory? Is that a yes or a no? Yes, right? But right now, I'm gonna show you the code that have these blocking problems. And what we'll end up with is you will basically go through each website one at a time. So let's look at a code example and break it down and see what is a blocking call, which is defined as the part of the program that has to finish before the next part begins. right? The part of the program has finished before the next part begin. And this is one question I'm gonna have you to think about while we are going through the code, which is, why is that bad for performance? So here is the code. Can you see my screen? Okay, so now this is what the function return. I want to print the number of times I see certain words, right? And right now it's anywhere. And this is basically word count, right? So to get this variable count, which is what I highlight here, we go to the line that produces count, which is line 26. Are you with me so far? Basically, to get line 28, we go to line 26. Yes, no? With me so far? So here, the line, what does it do? So the line basically tell us, say, hey, I want to map this function. Given the list of my URL. So this is my input. It's a URL, right? It's a URL. I want to use the function called counter, which is basically count the number of times the word the happen inside that website. Right? Basically, yes, map URL to a counter. It's a word count. Over here, we specifically just count the number of the 3-letter THE, right? So let's go through this function here, right? Counter. What does it do? And here's the list of URL. So our web URL is here, which is 3 websites. One is the English version of the Mahidol University website. The other one is apache.org, and the other one is the scalalanguage.org front pages, right? And we want to count them of these 3 websites. So the function basically does this. The first thing you do here is, well, first of all, is a URL. The first thing you have to do is to go get the text on that URL, right? You can do that by calling the function http get here, right? http get. These would give you the content of the website. This will give you the content of the website so that we can check how many times I see the word the. Are you with me so far? Any questions so far? And how you can do that is defined up there. And the only thing you do here is basically go get the content and convert the website into a string. Right? With me so far? Yes, no. Anything that are unclear here yet? Okay, I take long silence as it's still clear so far. The next thing you do is, well, I have the website now. I want to kind of like split this website into each word, so that I can count the number of the, right? I'm gonna break it down. So what I do is tokenize, which is basically called split. Like I have a string dot split will split the string, and right now I just basically split it based on the white space, any white space, right? Then you count the keyword. Basically, I have an array, and then I count that keyword. How many times I see the word the, right? So what's the problem here? What's blocking? So if you let me go switch back to the slides here. Oops, wrong way. Let me switch back to the slides, right? Think about the code that you just saw. And think about what can prevent this from being really, really fast. Because ideally, as we established, right, you can do all three web pages in parallel. Is this the case here? So basically, you will process each of the website, right? One after another. Yes, no? Yes. What do you so far? Basically, any question why is this not a great example of how to parallelize this? Yes, cool. Versus a better version here, which will go through them in more detail. Over here, you're basically waiting for the count keyword here to produce the number of count, right? To produce the number of count so that you can actually get the counting, right? You can actually get the counting. Any questions so far? Because if not, I'm going to proceed through the lecture. All right. So this is one example of the blocking call. You have parts of the program, for example, the part that you have to actually count the word, where you do it sequentially because you go through the string, right? Even though you have this in token of arrays of word, right? Of arrays of word. You still have to kind of wait until this is done before you can gather and collect all the counting, right? So to handle this blocking is, well, typically, as you've seen earlier, you can do it synchronously. What does it mean? Every time you see the word synchronous process, synchronous handling, it typically means I'm going to wait until the zero portion, the blocking call complete, so that I can run the next task, right? So what is the benefit here? So anyone can think of what would be the upside of doing it this way? Okay, I think the easier one is, what's the downside? Can someone tell me what's the downside of doing this way? Easy to follow. That's great. Actually, this is the benefit. It's easy to follow, easy to debug, and in many cases, if you run them 5 times, they're gonna behave the same way 5 times. Because you guarantee this will happen before this will happen before this is blocking this process, so you see the same result, right? Easy to develop, easy to debug. The downside is they are slow. They are slower, right? You can also do this asynchronously, which means that while we are waiting for the long function calls or something that block your process, you can switch to an independent task. And you can switch to an independent task. What's the benefit? It's fast, yeah. It fast, it increase what we call typically what I would call utilization of your CPU, right? You have a CPU is not doing anything, let them do something. I mean, come on, you buy a computer that has 4 processors while you having it run 3 things all the time, right? I mean, why not? The downside, this can be annoying to get it correct when you have bugs. Why is that the case? Let's say I have this thing where one has to finish before, like task one finish, then you run task two, and then task three, four, and five that are independent, right? And three depends on six. And somehow, I don't know what you did, but if you happen to run it in this sequence on where you finish task 4 before task 6, you run into a bug. But if you finish task 4 after task 6, your program will be fine. Do you guarantee that you will see task 4 finish before task 6? It's not, right? Because task 4 can happen anytime. And if it just happened to be after task 6, then you see a bug. Otherwise, do you run it the next time? You schedule task 4 first because it's not dependent on anything. So I'm going to run task 4 and then task 3 and then 4 finish. That's fine. Right? So this can be done in any order. So your bug might happen when you run it once, but the next time you run it, it disappears. Yay. Right? So this can be kind of hard to debug, right? Because at the end of the day, if you want to squash out the bugs, you somehow have to expand out this possible path and figure out what's going on when this sequence of execution happens. So when you do this asynchronously, you have to be more careful when you write the code, right? And there are many tools and many tricks that we can apply, right? To actually make sure that this doesn't happen. But we're gonna learn that later, right? Now we just want to do a high level downside, which is, well, it can be hard to debug, right? Somehow, same slide, my bad. Same slide, so I'm gonna go next, right? And before we go even further, I want you to know about the notion of time. And I think we all know what does time mean, right? What does time mean? Traditionally, functional programming doesn't really focus on the function or the notion of time. Anyone want to guess why? Anyone want to guess why? Do we actually think about what time do we run this? Remember our old I think I'm really not sure how many lectures ago that we talked about the state, right? Where you can store something and make it mutable. But the ability, actually, this is a benefit of functional programming, which is it's all data flow based. Basically, this function produce data for this function. This function produce data for this function. Do I even have a concept of time? I only know the dependency of this has to be finished to produce the data for this function, and that's all, right? But I don't really have the concept of time. This is along the same logic of why we don't have a state inside functional programming, because things are not mutable. Scala actually support this. Scala actually support this notion of time. What exactly do they support? Right? To encode that, hey, this variable, eventually you're gonna have the data. Eventually you're going to have the data, right? But right now, I mean, it's not there. I just want to declare it. Once the data comes out, you can use it. So this is a support that's called future. Future is a concept from I'm not parallel, from a programming language concepts where I'm gonna tie the data. The data is type T, so this is our data, and has the type T, right? And when I say future T, it means that that thing eventually they're gonna be a value. This is it. Basically, future of T basically will tell the computer that eventually you're gonna see something there. And the value can change into multiple states, But at the end of time, it's gonna have that type, it's gonna have that state, right? And when we request, hey, what's your data? What's your data? It can change. Basically, it allows the state changes depending on the time we request the value. Sometimes it's not even available, right? It just tell that, hey, this particular variable, this particular name, they are going to have something tied to that. And you can request it anytime. Right? With me so far. Any questions so far? So let's talk about the fact that future can kind of change, right? Depending on when we request the data. So in the simplest form, future can have two states, complete or determined, but complete computation of that particular value is complete, and it's gonna be final data. So this is like final. It's not gonna change anymore. I'm complete. I'm done. And then incomplete, which means that, well, the data can still change, right? And future, similar in a similar fashion to some of the type, right? The sum type that we learned earlier. Future is a container, it's a wrapper type. It represents that eventually this is gonna result in type T. Eventually it's gonna be type T. And the computation can go wrong. For example, I want to request a data from the internet. What can go wrong if I try to get a website, like if I go to, I don't know, facebook.com, what can go wrong? Is it possible that I'm not going to get anything back and got that dinosaur page in Chrome? Is it possible? Yeah, timeout, right? Things like your internet connection is not established, like your true or AIS internet decide to go down, which is actually more more often than you think it would be they're not ideal at all. Like they go down pretty often, right? So yeah, it can time out, it can die horribly, right? Um, it can many things in computer can go wrong, right? Many things can go wrong. So future will give you some exception of sort, right? So this is kind of like one of the assumptions that come with future, which is eventually there's going to be type T, but sometimes it might be timeout, right? So I will still wait for it, wait for it, and at some point when internet connection come back, I'm gonna get that, right? For example, if you open Chrome and you disconnect the internet, which don't do it right now, you're gonna see that dinosaur game, right? That say there's no internet connection, try later. And somehow if you connect the internet back, it will kind of automatically go to the website you requested, right? So conceptually this behave kind of the same way. Basically, I'll just say I'm gonna tell you in the future this will be available. I'm not I can't tell when. I can only tell that I'm gonna write the value once. I'm gonna write the value once. Once I write it, it's a final value, which is a complete state. I don't know when I can write it. Right? It becomes immutable once the computation is complete. All right, with me so far. Before actually, let's go through some examples. So hopefully make it more clear by going through our old friend Fibonacci. uh, we use this all the time because I feel like many class use Fibonacci all the time. So let's stick with it. By this time, you should be super familiar with Fibonacci. Right? So you can write it by, well, you can use future by saying this: import scalar.concurrent.future, and hint, concurrent means that this is something that you can use to allow many things to be run at the same time. Yay, right? So we are now migrating over from our concept of functional programming into the latter half of this class, which is parallel programming. These are basically something that also tie with the concurrency concept. This is basically kind of like handling execution context, and we can do something that's okay-ish, right? Any question about this particular implementation of Fibonacci? This is the traditional Fibonacci implementation. Any questions so far? I assume no, right? This is fib of n equal fib of n minus 1 plus fib of n minus 2. That's all. And with the concept of future, you can do something like this. Val f1 equal future of fib of 45, right? Fib of 45 will take a long time. Take a long time to run, right? But if I say this, val f1 equal future fib of 45, and then the next line I say val f2 equal fib of 46. Val f2 equal fib of 46. They'll actually be run completely in the background. Both of them will be running at the same time. You basically tell val, because val kind of force you to evaluate the expression, right? So the keyword val here kind of force your computer to get the value of f1 right away. Get the value of f1 right away, which means that you're being forced to compute fib of 45. The next line come in, f2 val f2 equals fib of 46. It also say evaluate this right now. So without future, it will first run fib of 45, finish that, then run fib of 46. But with future, you run fib of 45 and then fib of 46 at the same time. Any questions so far? So this is kind of conceptually, yeah. So yes, it allows you to run things in parallel, which is a really, really neat trick, right? So even better, when we migrate to parallel programming, we'll talk about a different language called Rust, which has a really nice support for parallel programming. It's annoying to get things to compile though, but it's really safe and really fast. So hopefully if you're looking forward to that, it's after the midterm. Uh, then the next question is similar to the sum type, right? You remember our sum of t, right? To access the content, you have to actually use certain function call, right? So future behaves the same way. So let's assume f1 and f2 are defined, right? F1 and f2 are defined. You can do something like this. F1 dot on complete, which is a really nice built-in function, right? I can just check, hey, whatever F1 is done, run this, right? And then another thing that you have to be aware is when you run things using future, it can complete, it can crash, right? It can complete and it cannot, basically it doesn't complete. So if it is done, case success, right? The keyword here is the capital S success, you pattern match to a result. This allow you to extract the value inside the future future data, and you can say print line result. If not successful, you can do something like this. Same thing here. This you have to import utility success and failure. This is a utility that allow you to do this particular pattern match, right? Future can be a success, which is success of D, or a failure of E. E is the error. E is the error. So when it fails, it will tell you what's happening. Basically, with future, if it fails, Once you complete, if it's a success, which is most of the time it's going to be a success, right? So you can say print whatever. You can do anything with the value right here defined in V. But if it fails, if something crash or something happen and I don't have the value, you're gonna get error. So you can do e.get message, e.get message, right? That's nice. So this is pretty neat, right? You can just use this concept and say, yeah, you can have the parallel program, and hopefully they're fast. We will actually learn why sometimes it's not fast. That's in the second half of the semester. This has to do with how you design the program, right? And we'll actually, toward the end of today, we'll talk a little bit about that, right? What can make it not as parallelizable as what you expect? And Fibonacci is one of the crappy function profile programming, to be honest. It's not exactly what I would call parallel. It's not too bad. It's not too bad. It could be worse. So since this has the notion of time, right? Since this has the notion of time, say if you want scale to wait for the future, but you know that, hey, I cannot wait for more than 1 second, right? If I cannot wait more than 1 second, say if you want scale to wait for future to become ready for a certain amount of time, you can do this. First, import concurrent dot duration dot underscore. Dot underscore basically means that I'm going to include everything in that library. And I can say await. This is another nice library to have that deals with future. So this is our future. Await dot ready means that I'm gonna wait for 1 minute. If they are ready before that, good. I'm gonna have the data. Otherwise, if it's 1 minute past and it's not ready yet, I'm not gonna wait anymore. With me so far? Basically, these kind of put restriction on how much time I'm going to wait for the future. So here's some use case. For example, an I/O call. What are input and output in computer science? Input and output can be network calls, anything that has to do with like getting the website, for example, the content of the website to show on your screen. These are I/O calls. Dealing with the devices on your computer, such as the keyboard, the mouse, the monitor, these are also I/O calls. Going to your hard drive, I/O calls as well, right? So waiting for this input, for example, I'm gonna wait for 10 minutes until someone type on the keyboard. If 10 minutes pass and no one type on the keyboard, I'm gonna skip this because no one may be likely to be using the input. So I can use await for that. Long computation, for example, I want to do a query on a database. Actually, there's a next example, right? If I have a database of, let's say, right now we are being hit by the pandemic, right? And one of the things well, the government is trying to do right now is to trying to figure out who has the COVID shot and who haven't got it yet. But those who have COVID shots, where and when would be their second shots, right? Which means that every time you want to look it up, it has to be maintained in some database. I'm not going to talk about how bad their implementation is. It's just a totally different story. And I have a lot of comments about that, but we're not going to talk about it. Conceptually, you have to make a query saying, hey, I want to look up the table and I want to go process this certain parts of the data, right? And because you're dealing with a database that contains many, many, many people, it's likely to be large. So this can take some time. This process can take some time. Future can be used to handle this long computation because, first of all, you can limit how long you're going to wait, right? Then you can say, hey, something depends on this future, go do that. While you are doing it, I'm going to use the computer for something else. It's just you unblock the blocking calls. You unblock the blocking calls. You can use it to implement RPC, right? Remote procedure calls. Anyone here heard about this keyword called Internet of Things, IoT? Internet of Things, one of the most common, like a true IoT in the, well, let's say you want to do a drone swarm where anyone here watch a video of, I think, Super Bowl halftime show 2 years ago where Intel has a series of drones flying on the sky and make it look like a firework, but it's not actual firework, it's actually drones that produce different lights. So basically, it's a swarm of drone, right? And somehow they have to communicate to tell, hey, I'm here, I'm here, I'm here, I'm here, I'm here. Move the position for this drone to this position. This position goes here. These drones are like they have a tiny computer built in on every single drone, right? It has a CPU, it has a hard drive, it has a memory, and they have a way to communicate through this mesh of devices. Right? It doesn't even have to connect to the internet. One of the really, really misconception about the IoT things that happen many, many times that I've seen is somehow people would assume that you have to connect to the internet, but it's not. Basically, Internet of Things means that you are connecting these things together into this like mesh of connection. RPC calls or remote procedure calls allow you to call a function from one device, device one, on device two function call. It's like you are asking your friend to do your homework. Is it convenient? Uh, the answer is probably yes. Are they going to be fast? Maybe not. Right? They are convenient. You can have the other device handle your own function call. Right? And the problem here is it can be long because it depends on the network lanes. It can be depending on many, many factors, right? So you can use future to represent the results of this. So I'm gonna do remote procedure call. At some point in time, I'm gonna have this particular data. In the meantime, I'm gonna do something else. You can use it to time out, right? So for example, I combine future and await. I'm going to wait for 1 minute. If this not back, I'm gonna do something. So this force you to return of no results or empty results on future of t. That would represent a timeout. I waited long enough, like 5 minutes. It's likely that your internet is down, so I'm not gonna run it anymore. It's gonna, because if I keep running these things, it's gonna waste your CPU time, waste the power consumption, right? So timeout is pretty important, especially when you look at mobile phone or like tiny IoT devices. How many people phone battery lasts for a day? And how many are not that more than a day? Phone battery is important, right? And if you think about it, the more you use the CPU, the more it drains the battery. In fact, whenever you have the data flip from 1 to 0, that takes energy, right? Basically, that's physics, right? They know that, yeah, it probably takes some energy to transfer data from here to the CPU so that you can do that add, that multiply. Everything costs some energy. If you don't have the timeout, it means that somehow your future is going to be trying to compute Fibonacci 130, right? And it's been 5 minutes. So I want to kill that process, basically. So it allows you to do that timeout. I'm waiting for long enough. I'm going to kill that. Don't waste my power, right? So this is another benefit of using future. Then now that we talk about future, I'm gonna talk about the other side concept called promises. Anyone here can define me what does promise mean in human language? What does it mean if I'm gonna promise you something? Which is actually supported in Scala as well. It guarantees that something is gonna be in the future, right? So a promise is basically that's perfect. A promise is a single assignment variable which the future can refer to, which means that with a promise, you're going to get a future. With a promise, if you have a promise, you'll get a future of T. Because you're being promised, you're going to get that. It's a confusing. Think back into human definition of promise, same concept. If you promise someone something, you will deliver. Eventually, there'll be a value, not the other way around. If you have a future, it doesn't mean you can have a promise. So promise, if you think about promise, kind of generate a future. That you're gonna have to guarantee you're gonna deliver that in the future. Same way as how we handle real life promise. If I promise that exam will be happening next week, I better deliver that. If someone promised something to you, they should honor it in the future. If I promise you something, I should keep the promises, right? If not, I'm an asshole. And sometimes I just, which is bad, and I feel bad. I'm sorry about like making sure the assignments are great by certain dates, and I missed that. I'm so sorry, guys. But this is basically the definition of promises and future. And to realize the actual value of future versus promises, right? To actually use it, right? I mean, so far these are good ideas, right? So far these are good ideas. But if you are looking at the hardware, it's plain and stupid, right? If you are interested in hardware, I would, I guess, PR for a potential class that is on the curriculum, which is the extension of the ComSys arc, which is just flat computer architecture, right? This is the extension of the ComSys arc, which can span into OS, network, and architecture. I'm going to talk about how to design hardware. And the key thing that you're going to learn is hardware can be plain and stupid. There's a big gap between how do you fill in that gap to make the hardware less stupid. So there's a lot of concepts in computer system, compiler, programming language, and architecture to make sure that this concepts of future and promises can be done and implemented inside, say, Scala on your computer system. So why should you care? Why should you care? Is that, again, this slide's a little bit side topic, but I want to bring up this discussion that while you have this really nice construct, this really nice concepts, right? There's a lot of work done underneath to make it work. So the reason behind this is like this bridge, the abstraction between your program to the runtime and then to the hardware, right? And the next slide, I will not put it on the exam. So this slide and this particular topic will not be on the exam. Why is that the case? This is something that will be covered in the system class, the ComSys arc on the OS part. It's the concept of the thread pools. So if you took OS before, if you took the ComSys arc right now, you might have seen this, a thread pool. What is a thread? Think of a thread as a process. Like you, how many of you have 20 Chrome tabs opening? Or 10? Yay. So you realize, right, that you can kind of operate each tab by just clicking, and they'll basically render the website, show everything that you want to see. If it's YouTube, they'll show the video. Somehow in the background, you hear the noise, right? If it's Facebook, it will keep updating your friend's life story. Sometimes you want to see it, sometimes you don't even want to see that. It's too much information, right? So each of these tabs, generally they are one thread where a thread gets mapped to the CPU. So let's say you buy an 8-core CPU, right? They are actually capable of only running 8 to 16 parallel things at once, at any given time. The system, which is your Windows and Mac OS or Linux, will figure out what thread, which is think of it as a task, right? What tasks get to run at what time. The thread pool is a collection of this thread that are idle, like, hey, I'm not running anything, but I can get work. So basically, you can assign work to and implement the thread pool to handle creating the worker, manage the worker, and schedule the task, right? This is actually an active area of research. You can have event loop. That's basically, it's a loop of event, as the name suggests, right? That can be used to handle certain things like a file system, like you go to the hard drive, right? One thing that you might not have realized about going to the hard drive is it's actually takes a lot of time because a hard drive also involves mechanical parts. Anyone here seen like the inside of the hard drive before? That has this disk and this pin that go around. So hard drive is just layers of disk, right? Think of this as like your old friend CD-ROM and DVD, right? And there's a reader that go around to read the information, right? So when you actually have to go read the file, there's an actual mechanical pin that you have to drive around the hard drive to figure out, okay, it has to go to this angle, read it on this disk for this length to extract the data. And that can take certain amount of time. It would take longer time than doing an add or multiply, right? So this allows you to kind of like use an event loop where you decide to handle like reading files, going to the database system, or using web services, right? These rely on the implementation of libraries and framework, and you can use future and promises for this thread pool and event loop. So let me double check my sample code here because I believe I have it. I want to, if I have them right now, I'm gonna show it here. So give me a few minutes. Here. Oh, it's in Rust. So let's wait until we learn Rust and we come back to this. We come back to this and see how we can implement it. So I have the code, but the code is in the language for our second half of this class, which is called Rust. So once you're a little bit more familiar with Rust, I'm going to show you this particular code, right? And you can utilize the concept of future and promises by unblocking things, right? This is basically the whole idea. If you don't remember what we're learning today, remember the slides. Remember this slide first. You want to be able to unblock things. You want to be able to use it to, for example, pipeline program execution. What is pipelining? Let's say I need to finish task A and then task B and then task C, right? I can do this. I can finish task A first on CPU 1 and CPU 2. I would wait, but then I can do task B here. And in the meantime, CPU 2 is available and can do task A prime, right? And then this is task C, this is task B prime. The next set of pipeline program execution, right? So let's actually look at our program from our example earlier and see how can I make it faster. Okay, so let's look at the code here. So do you see the new code that say object future hello world extend app? Is it out on the screen? Yes, no. I just want to double check the use. Okay, cool. So you see the import here. I import duration because I have to do something has to do with time. And then I want to use await and future, which is the two data type that I'm gonna basically I'm gonna implement the code based on, right? And then these two are the same thing. I want to be able to process the URL right here. Get HTTP get give you the URL This is basically making sure I have scale at the time. Over here is the map function that would actually count the right? Count the. But I can use future for that. I can use future for that because now I have, let's say, 4 websites here. I have 4 websites right here, right? This is a vector, basically it's an array. So I'm gonna do this. A count, this count is going to be the future, the array of vector int, vector int. I'm gonna go do this on all the 4 websites at the same time. I'm gonna do this 4 websites at the same time. I'm gonna traverse here, right? By calling the function, this is the function I want to call. Counter. I just want to count the number of THE, right? The same function call. This is the input. This is the input. Future.traverse basically allows you to apply the function counter here on the input, which is over here, web URL, right? So basically I apply the function counter on web URL, but I'm doing it concurrently. And here is a function call, right? Here's a function call. This is our input, which is the URL, right? URL. The first thing I do is I do HTTP GET. So if you look at HTTP GET, what's the return data type here? It's highlight on line number 9. What's the return type? It used to be a string. What's the return type now? It's a future of string, right? The reason why it's a future of string now is I have 4 websites. I have 4 websites. Do I need to actually wait for the first website to finish before I run the second website? Yes or no? No, that's a perfect answer, right? So what I can do, I'm gonna go get the URL on each of the website. I put that in the future because eventually they'll be available, right? Eventually it's gonna be available. So it's a future of string. These basically guarantee, future of string just guarantee that this HTTP GET, it would take some time, but you get a string. And with that, what's the type of content here? It's not a string anymore, right? It's a future of string. So what do we need to do to access the string? To access the string, then you do content dot on complete, right? Because it's future type, so you do dot on complete. If it's done, you print and you basically get the tokens, right? You get the tokens and tokenizing here, you basically this allow you to extract, right? That hey, I'm gonna tokenize my URL. Here, it's a function call again. Content is a future. Remember, content is a future of string. It's a future of string. You map. You map the content and tokenize it so that you get array. Basically, it's an array of a string. So that at the end of the day, once what's the return type here? Content is a future of string, right? This is a future of string. Tokenize return what? So eventually this input is going to be a string, but when you do this, it's a future.map. Tokens basically is also a future. This is a future of a string vector. Basically, it's a bunch of string. So you say tokens.onComplete. Once I finish the tokenizing, I'm gonna start the counting, right? Counting the keyword the. Right. Again, once this is done, right, it's going to return a future. Right. So count here, count is a future. It's a future of an array, and the array is going to be just the counting of the number of the in musc.mahidol.ac.th, in apache.org, in scalarlang.org, and in wikipedia.org. And because we have a future, we want to actually extract it to an actual integer. You can say, hey, I'm gonna do this counting, but I'm not gonna wait too long. I'm gonna wait only for 10 seconds. Right? I'm gonna wait only for 10 seconds and see how many, like what's the count so far, right? And then print. All right, any questions here? Basically, over here, we use future everywhere. So every time there's a chance that we can actually do things in parallel, or that's a long running process, like go get that web URL, right? That can take a while. This, we use future, such as here, to get the URL, we use future for that. To process the web URL over here, we use the future for that, which is right here, right? And then we use await in order to wait for the result for 10 seconds. Once we have all the results, or once 10 seconds is over, it will print the count. All right, so that's it for future and promises. I'm gonna now move on to and transition basically into parallel programming by talking a little bit about concurrency and kind of motivate you over on what does it mean to be running things concurrently. By the way, this is this is the end of content before midterm, right? So anything we cover so far until this slide can go into the midterm. Concurrency, that's for the final, right? So now that we talk about asynchronous program, like future, we want to be able to think about, okay, can we actually run this in parallel, right? What does it mean for a program to have concurrency? And what does it mean for a program to be asynchronous, right? And why does the programming model fits kind of well here? The key I want to say is look at the data flow paradigm, right? The first lecture that we cover. What is exactly a data flow paradigm? Can someone tell me what's data flow? I hope you're not sleeping because I somehow put my cat to sleep. She's actually snoring right now next to me. Yep. Data flow is basically the way you think about the construction of the program by looking at what inputs are coming and whether I have the input ready or not. And then you can fire off the operation, right? So whenever I have all the input ready, I'm gonna run it right away. Why is that good for parallel programming? Anyone want to take a guess why data flow is really good for parallel programming? So if I look at this, right, So that's a good answer. But if you kind of look at this example, what can be done in parallel? What can be done together? So the first add and first multiply, right? It has nothing to do with each other. I can clearly see, right? Hey, I can do those two right away. Yay, right? I can do those two right away. This allows you to actually process the data right away. If you write things in data flow, you know which are ready, right? And you can make it run in parallel. Uh, so the code example is now on Canvas, the web URL that we just saw earlier, right? We already break it down, so I'll skip over this. Now I kind of want to talk about the concept of multi-core processor. Anyone here have, well, I'm sure you all have a laptop, mobile phone, or a tablet, right? Otherwise, somehow, I'm not sure how you join this particular lecture, but have you ever wondered, so what's the benefit of having multi-core over, say, a faster, like for example here, remember Pentium 4? We are looking at like 4 gigahertz CPU, right? If you think about it, right, I can have 4 slower core or one single fast processor. Or anyone here heard about the M1 chip from Apple that used to power the MacBook right now? That computer basically has something like this: a big CPU, a smaller CPU that attached to it, right? And so let's abstract it this way. So if you have more transistor on this big CPU, basically means it's faster. So you have this really fast CPU and slower, but 4 more CPU. What could be the benefit over, say, a design with 2 big CPU? They might take the same amount of area on your motherboard, right? That's the limit. That's the physical limit of what things you can put on a chip. So let's say, what's the benefit of having this left thing versus the right thing? That's a great answer. So that's one of them. Smaller CPU actually consume much lower amount of power. So much lower. The story actually, and yes, you can run many things. So those are perfect answer. The large, that's also a really great question. Everything here is a yes. The larger one would run faster, right? The smaller one would be slower. But if you have, say, 20 core up, sorry, if you have 20 tabs on your Google Chrome right now, do you want the left processor or the right processor? The left one, right? Because you want to assign the first tab on one of the CPU, the second tab on the other CPU. So basically, you have 5 CPU to run each of these threads, right? Rather than a lightning fast, only 2 CPU, right? But let's say you need to do a really heavy complex math operation. Do you want the left one or the, well, actually, complex math operation that you cannot run in parallel? Do you want the left side or the right side? You want the right side, right? That's why I say Apple M1 come with both of them. Because if I know, okay, this thing need to be really fast, I'll put that on a big CPU. If this thing, oh, I can run in parallel, I'll put that on a 4 small CPU. You see the benefit now, right? That, hey, I can pick the scheduling part. That's the complex part. Like, how do I pick? That's a totally different research problem. But it gives you the room. Like, okay, I have the lightning fast CPU and a bunch of multiple parallel CPU, right? Back in the day, so the reason why I said the all your question, all your answer are awesome because everything is correct. The first thing is the big CPU consume a lot of power, right? It doesn't go linearly. As you increase the CPU, it's actually go exponentially. So it's actually not exponential, but it is polynomial, right? You go that way in terms of power consumption. There was a running joke that if you keep up with the clock speed of the CPU, say 10 gigahertz, 20 gigahertz, at some point you might need a nuclear power plant to power your CPU because it consumes so much power. So that's one of the concerns of having large CPU. That's also why, when you think about it, the GPU consume a lot of power too, right? But for a totally different reason. GPU is a lot more like a tiny little CPU that's attached to each other. There's 1,000 of that. It's different. But they consume power. The second thing is sometimes having a large CPU doesn't mean it's actually faster. It can be faster, but the benefit plateau at some point. The benefit is not like that much higher. It's not like linearly going up, right? You need to think about how you actually design the hardware to get that benefit, right? And there's also another problem about your program that you're running. Can you actually utilize all the cores? So let's say I have a design with 8 cores, right? All right, my cat is snoring really loudly. It's funny. I'm not sure if you heard it or not. It's next to me here. Uh, so if you look at this 8-core processor, what will happen if you ended up using 4 of them? Let's say you run like 2 programs and both of the program is not that parallelizable, so you have to actually you can only run 2 things at once, right? What does it mean? Do you need to waste your money to buy that 8-core processor, or are you good enough with 4-core processor? So do you prefer saving money in that case? Right? So that's true. So it's also about the design of your program, right? Can you actually take advantage of, say, the multi-core processor? Another common example that is actually true that happening right now in how many of you here heard about Thai Supercomputing Center? If not, actually, let me show you. It's a really awesome project, actually. So Sawattasha or NSTDA actually have now they built this high performance computing center that consists of really powerful cluster of CPUs and GPU, right? This allows the research community in Thailand to actually use it to do something awesome that are meaningful, right? Hopefully way more meaningful than a lot of the like not so impactful projects that are happening in Thailand because we don't have enough compute resources. But it just happened that sometime, right, when you write a program and run it on this cluster, if you forgot about parallelisms and you say, hey, I want to book 16 CPU core, but your program actually use 1 CPU. That sucks, basically. So when you write a program, always, please think about how many, like, can you parallelize your program? Can you make it really fast? If so, do you need it to be fast? If you need it to be fast, please make sure they're fast. And the law that kind of dictates the performance, we call it Amdahl's law, is like this. One of the things that we care about in every development of both the hardware and the software side is what we call speed up. So if you just see the word speed up, can someone tell me what do they mean in English? What does speed up mean? Yeah, do the ability to do something quicker, right? So what Amdahl law say is, and this actually happened back in the days of a while ago, right? That's when the hardware community was like, we should have multiple core, we should have more and more and more parallel processor. And Gene Amdahl comes in and like, yes, but don't forget about this. The more processor you put in, it only benefit if you can have parallel parts of your program, right? So your algorithm dictates how fast you can be when you buy a multi-core processor. So these can limit the benefit of two things: parallelizing your program and parallelizing your processor. The serial portion of the code, the part where you can't really break them into parallel tasks, it can be critical to performance. And surprise, it was actually a law basically written onto the paper about 50 years ago. That's how long this law has been around. And it's still important today. It is so important because when you write the program, there's going to be what we call critical section. Critical section is the part of the program that you write that requires blocking, synchronization, barrier, anything that are requiring you to wait, right? And with the classic 1967 definition of Amdahl's law, it doesn't really mention this, so let me break it down here. Critical section can be broken down into kind of two cases. The first one is what we cover today with synchronization, right? Blocking processes, for example. Sometimes it's come without synchronization. Over here, right? This is one example of critical section. You have sequential part, and here is a critical section where you have still a parallel parts, but all those parallel tasks, the 7 blocks here, they all have to finish at the same time. They all have to finish at the same time before you can resume and run the next part. So this is basically can be dictated by, for example, the algorithm, right? You can parallelize them, or the algorithm again, you can parallelize them. It's 7 threads, but it has to wait at this barrier. Right? Another common type is this. You have this share variable, right? For example, you can have a shared linked list, right? That can be a critical section. For example, I have a shared linked list where every thread can modify that. But if I modifying that linked list, no one else can use it because I want to make sure everyone see the correct copy of the linked list. And I'll give this example. Let's say I'm poor. I have the money in the ATM, but I only have 100 baht in my ATM. I'm so broke right now, right? What will happen if I go to the bank and someone stole my ATM card and both of us try to withdraw 100 baht? What do you have to guarantee? Well, you have to guarantee that only one of us get 100 baht, right? Because otherwise the bank lose money. So that account is a share. Think of it as it's a share variable because I like the only one transaction can happen, not both of them, right? Yeah, it should be one by one, right? One transaction has to happen and finish completely before the other one can begin. So this is another critical section because it's a share variable. If someone want to write or modify that data, everyone should wait until you see the changes. This is important going forward for this class because Rust the way you can parallelize things also dictates by this particular share variable too. I would like to thank the paper. I basically borrowed the paper from this paper in ISCA 2010. The paper actually talks about how we can extend Amdahl's law, right, for multi-core. It's actually a great paper. If you're curious about it, feel free to check back with me. ISCA is the basically top paper outlet for architecture. Basically, where the best paper in the world go to. Yeah. So that's it for the class today, actually. We have about 20 minutes left. I'm going to be on Discord to do a Q&A like usual. Let me save the annotated slides. I already got one request about the annotated slides, so I'm going to likely put it on the Canvas website, the class website. I'll figure out how to make sure it's not cluttered everywhere. So yeah, I'm gonna post those on the slide as well. Don't worry. And that's it for the class, the lecture part today. And I basically let me stop the recording before I switch over to Discord. All right.